useful and how we talk about this before. So first we would like to just see if I can enlarge this. Is it visible? It's okay. The idea here is that we are going to consider a problem of analyzing satellite images. And satellite images are useful for various purposes. So people have been using them, for example, in insurance topics such as risk modeling, damage assessment, high-value assets monitoring, and so on. They can be used for example, in precision farming, so they provide data on the land, and with this information we can make a more efficient use of valuable resources, for example, fresh water. So we can be more efficient in farming. For example, in forestry, so we can use them for monitoring fields, growth rate, and so on. Of course, we can do monitoring on infrastructure, various things. Let's say there is a company which has its pipelines, for example, and it wants to monitor it. Then satellite images can be used for that purpose. We have natural environment monitoring, transportation, improvement, asset tracking, and so on. So there are a number of real applications where this information from satellite images is useful and can be of some value. Okay, so for different companies or governmental institutions and so on. So an example of how these images are processed or what kind of information can be extracted from them is that actually I took it from this paper. So the problem of land use and land cover classification. So we want to perform some kind of automatic analysis of satellite images. These satellite images are usually quite large. They contain a lot of information. And the problem is that usually these objects of interest are quite small. And it's very difficult or time-consuming to do it manually by a person who is just sitting and trying to analyze these images. So we want to have computational automatic methods that can extract this information from these images for us. So for example, in this case, what we do, we have a satellite image, and we know that we are interested in some classes or categories of land type. So for example, we are interested in industrial areas or rivers, highways, residential areas, these kind of classes of land, which can be, of course, used for further analysis. So this is not just to have this classification, but for example, we are reconstructing a road network, right? So we want to have an image of some area, and we want to reconstruct automatically the road network for some purpose. So of course, then we need to first identify these parts where we have a highway or we have a road. So then we perform this kind of analysis and we extract these parts of the image which are of interest to us. And this process or this analysis is usually done with some computational frameworks, with some computational methods that allow us to extract this information. So the workflow is the following. We have a satellite which is gathering the information, taking the pictures for us. Then once we have a good quality picture, this is quite crucial here, so once we have this picture, we can feed it into our model. For the moment, I'm just symbolically showing a neural network, usually some neural networks, or some other computational model, which allows us to perform the analysis and extract the relevant information. So for example, this part of the image is classified as, this is the output, it is classified as an industrial area. Okay? So this is the idea here. However, the problem is that this is an ideal situation. So the thing is that we get images which here, for this analysis, which are good quality, and let's say they are kind of normalized, pre-processed, but still the images are of good quality. The problem is that often this is not the case. And one of these reasons why the image can be not so good is simply there could be clouds or some kind of fog or a disturbance which does not allow us to directly perform the analysis. And this is actually a quite big problem in analysis of satellite images, the presence of clouds. I mean, we have satellites, we have instruments to take these pictures, but the problem is that such an image is basically of no value because it is covered with clouds. There are, however, techniques of removing these clouds, or maybe not completely removing. If the cloud is thick, if it's large, there is not much we can do. But if it's kind of tiny or not so thick, we actually can do something. And this is another point where computational or computer science techniques come in place, because we can use a technique, or generally termed data fusion. So we will take data from different sources, and we will try to put them together in such a way that what we get as an output is something which is of enhanced quality, enhanced value. So there is more kind of information than from these single data sources alone. And how this is done in the case of cloud removal, well, what we can do, we can take our standard optical RGB image, but we can also use another instrument, some kind of a radar, which actually does not provide us with visible optical information, but with some kind of other wavelength information, which actually can penetrate the cloud. So, as you can see, maybe, I'm not sure if this is visible, but it's in this image, and what we will see in this course is a case study where actually two types of information is used. So one is the RGB image. Let's say these are 3 examples, so each example is in a separate row. So we have an RGB optical image, and then we have NIR, near infrared radar information, image, also image, but this is not really what we see with our eyes. It is a different type of wavelength, I mean different wavelength image, which actually can penetrate through fog or through some not very thick, let's say, clouds. So actually we can get some kind of information about what is underneath, what is on the ground. And the question now is, or the task is, to combine these two sources of information in such a way that we get an image which is of better quality than the original RGB image, and that can be used for further analysis. And actually what we want to show you is a case study, I mean basically a project or a system actually, which can perform this kind of data fusion of two information sources, coming from two information sources, which allows us to improve on the image and get something that can be used for further analysis. Okay. So this is what we are going to look at, and actually this system is quite involved in the sense that it uses something which is called, I mean, it will use neural networks for performing the task, but these neural networks are quite advanced. I mean, these are so-called generative adversarial networks, so you will have not one network, but you will have two networks. And these two networks are going to be trained against each other. Okay, so far you haven't seen maybe I ask a question, who is familiar with neural networks? I've done anything with two person, okay. So the thing is that there are two neural networks, quite complex, which are trained against each other, and the idea is that we basically have two, this is like a game between these networks. So they are trained against each other, they play against each other, but in a way that allows us to train one of the networks in such a way that it will do what we want. And you can think of this, I will not go into much details of that at the moment, so I will introduce neural networks slowly, but just to give you a kind of intuition on how this, our target system will work, is that we have some kind of an artist and an art critic. Okay? So the artist will generate the image given these two informations as input, and it will try to fool the other network, which is the arithmetic. And the arithmetic's role is to distinguish whether this is a, let's say, good or bad image. Okay? So usually the arithmetic will try to say that this is not so good, not so good. And the other network, or the first network, the generator, will be trained to fool the discriminator, the arithmetic. So it will, each iteration, it will generate more and better images. Of course, the other network is also trained to make better distinction between these images, so they kind of are trained at the same time against each other. At some point we will stop, we will take this generator network and then apply it, as it already is trained, apply it to the data, and we will see that actually we can do cloud removal. And if this is visible, or maybe not that much, but hopefully you can see it on your screens, if you look at the notebook, that this is actually done for new, the images which were not used for training, actually new images, where you had the clouds, you had this paired, let's say, NIR information, new infrared data, and with this fusion, we were able to remove, actually the system was able to remove the cloud. So you could see the outcome is here, and this is for the three different cases. Okay? So this is the main idea of how the system works, and what we are aiming for, what we want you to show, and we want you to understand how, at least on a, let's say, high level, maybe not every detail, but on a high level, how this system works.
So can I ask something?
Yeah.
In this case, what's the labeled data and what's the unlabeled data?
So the labeled data will be that you have the input, so the image with the cloud on, and the NIR image, and the ground truth will be the image without the cloud. And then the training is done so that the discriminator will be learning so that it can say if the generated image is close to the real one or not to the real one. So the label is, it's not like a class, it's more like that's why I said that the network is more complicated than the usual neural network, but we will see it later on, next week, what is the architecture of this network. For the moment, I will go step by step through how, in a simpler case, how a network can work, how can we train a network for also a space-related, let's say, a project, but you get some understanding, and then we will see how these labels, as you said, can be transformed to images. So how images can be used as labels, but then we'll see next week, because this network is, for image analysis is more complicated.
Before, if I may, so at what stage of the project do we provide the neural network with cloudless images, with images that are already cloud? How does it know what a cloudless image looks like?
So we will see that in the project that we will actually generate clouds. So we will generate data, like images with clouds, and these images will be used for the training. So we will have all the full information. We will have image with cloud, image without cloud, and NIR. So this will be used for training, and then we can take real image once the network is trained and use it for to remove clouds. There was one more question.
I was curious.
Uh-huh.
How would you, so based on what you've just discussed, what should I take away from that? If I were a student, what should I take away from that? Is it something, is it just you're giving us an example and then we're going to work into it to understand it in more detail, and that's where I'll get the part where I'll be assessed on, or is there something here that you've already discussed that will be used for assessment?
For assessment. So the idea is that we will present this system for you to understand the idea how this is built, how it works. And the assessment is the idea was of the assessment that you kind of have some kind of an interaction with the system. You will play with it, you will change some parameters, and you kind of write a short report on all your observations on that system. So you understand the purpose here is more to understand the concepts and to understand the building blocks of these neural networks of the system, and see how it behaves depending on some meta parameters that you are going to work with. This is the idea of the project that we will see next week. Okay, so this is the motivation why we talk about I mean what will follow. You should have this introduction in mind that we are going towards this quite advanced system, and that we want you to kind of understand how this system works and how can you later on, when you need, adapt it for your purposes. Because this system actually, these networks can be used for other problems, other tasks, and then you kind of can use this as a skeleton. So you have a skeleton with the architecture, and you don't need to code or build it from scratch. You can use it, and if you understand the principles, you can adapt it to your problem much faster than, let's say, building the whole stuff from scratch. Okay. So this is what we have in mind, and now what I want to present is go slowly first, and because as I told you, you're maybe not that familiar with neural networks, so I will try to explain what the neural networks are, how can we build them, and how can we train them for a particular task. Today we will see a task which is a bit simpler, so we can kind of comprehend how this, all the concepts and how this whole thing works. And then we will see a more advanced system where actually the thing is that you cannot really analyze it through them. You will be given some architecture and that's it. You cannot really analyze every piece of it because it will not give you much more insight, but we will see it in a moment. Okay. So, where all this comes from? So, of course, we are talking here about artificial neural networks, and the inspiration for this computational framework model is, of course, stemming from biology. So, if we take, let's say, a human brain, there is a network of neurons, and these neurons. I mean, the capacity or the number of neurons is about what is called here is 100 billion, roughly. So these neurons are, in fact, quite simple. If you think about it, I mean, abstracting from, of course, from all the biology, but just how this neuron works. So these neurons, they communicate. This is the main idea. They receive messages and they forward these messages to next layer of neurons. And this communication is done through the interface, which is, we call the axon terminals and the dendrites. So you can see a picture here. So we have these basically dendrites, which are inputs to the neurons, so other neurons are connected to this one through the dendrites. Then some processing is done here, and if some condition is satisfied, the signal is forwarded to the next neuron. Okay, so the neuron gets activated and then transmits this information further. So this is how our brain works, and we know that actually with these simple, as far as we understand this, with these simple things, our brain can perform quite impressive tasks, right? For example, we can do image recognition, right? I mean, we recognize faces. It turns out that this is computationally quite an involved problem, but the building blocks are relatively simple. And actually, this has been, so this is like a more picture where you see the biology or the names and so on. This is more simplified view where we abstract the detailed information and we only are looking at, okay, so what is relevant from the point of view of the functionality of this element. So we have the dendrites which receive the information from the, let's say, environment, from other neurons. And then we have the axon, which is transmitting. If the neuron gets activated, it transmits the signal and transmits it to the next layer or next neuron, which will continue with the process. Now, how can we, if we want to get inspired, we get inspired by this, and how do we transform it into a mathematical or computational framework? Well, we consider the artificial neuron. And the artificial neuron will be the basic building block of all which will follow. So this is quite simple. So we kind of mimic what happens in biology. So what we say, we have some inputs. So these are our inputs to our neuron. And then what the neuron does, with some weights, it simply sums the signal, which is coming from the out sources. It sums it. If needed, it can shift it by a number, so it just shifts, adds a bias. And so far, this is modeled as a affine transformation or a linear transformation. Okay, so we have seen that this is just addition of the like weighted summation plus a shift if needed. And finally, what we can do if we want, we can also put something which is called activation function. So once we have computed the sum, we can apply the activation, and this is what is output from the neuron and sent to the next layer. You will see the layers in a moment. So forgetting about the mathematical details, we can say, okay, so technically it's just some numbers coming in, we sum them, we add the bias, and then we see if this this value exceeds some threshold, which the threshold is defined by this activation function. If yes, the neuron gets excited and it basically transmits this value further. If not, we can have, depending on the activation function, we can have different behaviors. We can either send zero, nothing, or we can send just some smaller value, whatever. So this really is up to us. Okay, so this is the basic building block of any neural network. But of course, what we want to do with this, we want to train the network. Okay, so we will build a network from these neurons. For the moment, we can think only about one neuron in our system, because I didn't explain how the network is built at the moment, but let's focus on one. And, yes?
Is neuron always following this formula?
Yes.
Always.
Always.
So there's only one kind of.
Well, it's kind of general because I didn't specify what the activation function is, and there is a number of activation functions. But in general, this is the, let's say, the generic form of a neuron. So it sums the signals, does a linear transformation or affine transformation because we have the bias, and then on top of that, it applies optionally and non-linear function. This will be crucial, but we will see it in a moment.
Just compared to what we were doing before, I think we were doing until the part of the V, right? We were doing the prediction before because we were having inputs of X, we were generating our both omegas,
Yes.
and then we were having the prediction, we were calling H, but now it's V, I suppose the same. We were not having the activation part, but I think we went until there.
You went until, yes,
Yeah,
exactly.
okay.
And this is the part where you will see it, so you see the connection now with what was previously. Because we are going to train this neuron. And the training means that we want to fit some experimental or input data. So we know some, let's say, inputs. We know what we want to have as an output. The problem is we want to set up these parameters. What we don't know is the W, we don't know the bias. Okay, so let's say all the W's are parameters for this neuron. And this is the place or the moment where this gradient comes in. So we first have to define our loss function. So this maybe we have here. So the loss function is measures the difference between the input data or the, let's say, we take one sample. So we have a pair where we have the X coming in and we have the Y as the output. And we want to fit our neuron to that. So we have to measure. Okay, we have some initial, let's say, values for our parameters. We give this input to our neuron. The neuron computes the output. And then we have to compare what is the difference, somehow measure how good our neuron is in fitting this data. Okay? And I have prepared, if you are more interested in this, this is basically the mathematical formulation with the notation you have seen so far, but I will not go into these details at the moment. You can see this is kind of an appendix to your notes at the end of the lecture notes. So this is actually how the loss function is calculated. But this is quite involved, so let's for a moment, just to have a overview, we don't really go into maybe this much details, but just imagine that you have a function which allows you to measure the distance. So what you have seen previously, once you have a function, you can try to optimize the function. You can try to find a point where your function reaches a minimum, let's say, value, maybe not global, but local minimum. And for that, so once we have the loss function, actually we can do it. We can compute the gradient. And to find the optimal solution, we can apply the gradient descent algorithm, which you have seen previously, which is used to train the neuron. Okay. So again, we have the neuron. The neuron has the parameters, W's, and we don't know these values. We don't know what these W's are. So we have to train the neuron with our given training set data. And to assess the quality of the training, we have the loss function. And we have the loss function mathematical, when we have this gradient descent algorithm, we can now optimize our parameters so that our neuron or model in general fits the data. Okay, so this is the idea here.
No, when we are actually trying to improve the neuron, so we are just playing with number 2, that is sum up, and number 3, activation. Are these the two parameters that we are trying to change?
So activation is a function. Let's think about, you could have a given function. So the function is, once you have specified, it's fixed. So what you get to this function is the argument. The argument comes from this summation. X's are input, so these are given, but W are the parameters. So what you are training, what you are trying to solve for, is to find the values of W such that, so all W's, so all which are in the summation and potentially in the bias, and the bias could be 0, but this is going to be trained. So you want to find such a values that whatever your input data you have, when you give your input data, they are fed and you receive your output. This output is as close as possible to the output you have in your data. So you compute the difference between the output given in your data set and the one which is computed by the neuron. So you want to be as close as possible to these values.
How is this related to curve fitting?
How is it related to curve fitting?
Sounds pretty
This
simple.
is basically, let's forget about activation. This is regression, linear regression. So you basically do linear regression. So you have points and you try to fit a line which fits your, so this is like let's say it's the simplest or very trivial case when you, instead of a curve, you have a line which you're trying to fit. Once you have activation, this becomes nonlinear. So in fact, what you do, you fit a curve. So it's basically a curve fitting problem.
Why did it exist as a concept long before machine learning came out? It's just that it's basically curve fitting with a massive amount of data?
Massive amount of data and massive amount of parameters. Because if you have curve fitting, usually previously you had a few parameters, you will see in a moment that these will go to millions easily. So a neural network, for example, the one we will see next week, has millions of parameters which are going to be fitted. And of course, for that you need a massive amount of data. And this we'll also see in a moment how do you deal with this, because it's not that trivial to fit the model to such massive amount of data. So you need massive amount of data because you have a massive amount of parameters. But this fitting will take a lot of time. You need a lot of iterations. So this will be, we will see why is it challenging. Okay. So, and maybe one more remark. Okay, so this activation function, this is already kind of, this was answer to your questions in a way. So, if we would not have this activation function, basically our neural network would be a linear transformation. So even we would have more neurons, like if you have a linear function and you combine it with a linear function, what you get is a linear function. So no matter how many layers, combinations we would have, we would finally end up with a simple linear function. And of course, a linear function has there are great limitations. We cannot really fit anything. Only linear problems can be solved with such an architecture. That's why we need to have a way to introduce non-linearity to the model, and this is done by introducing the activation function.
Could you maybe use an example for a linear problem where we wouldn't have to use machine learning versus a non-linear problem? In real life, what is this?
I have actually prepared something like that. Let me just check the time so I see. Okay, so we have. I will show you because I have. This is in the lecture notes. I have it basically a little bit down. So maybe I can finish this and we will go so that you can actually play yourself with the net. So let me just present you all the steps so that we get to a point where I can come back to it.
Can you zoom in a bit?
Zoom in.
Yeah.
How do I do that?
Control plus maybe?
Ah,
Control plus. Yeah.
Control plus,
Or command plus.
command plus. Yeah. Is better? Yeah. Okay.
And do you have an example of the matrix implementation of the loss function for Python? I tried to do that myself and I had trouble with the dimensions and getting the,
For the, you mean for the loss function?
yeah, or for a generic loss function, basically, for the,
So I have for the linear, I put it in the, it's also in the appendix, so I put some material. Okay, this is not this one, it's basically here, so I explain the layer. So you have the very simple example here. So maybe we could go after I go to the material, we can go back to that and I can
By the
show
way,
you.
so we are going to have like a framework for all these operations, which is like called chainer here.
Yeah,
So you don't need to do it with like a NumPy.
okay,
So yeah, we have better tools for it.
okay.
Mhm. But I will explain in
Yeah.
more details. If there is time, we can discuss, I can show you how to do this. So, okay, so let's quickly go by step through the elements again of the neuron. So what are they? So that we have the basic element somehow well understood. Okay, so we have inputs, and this is of dimension, it's basically a vector of dimension n. Okay, so n inputs, n numerical values which are given on individual dendrites, let's say, into the neuron. So this is our input. And of course, we will have many such inputs because in our training data set we will be given the inputs. So we have n, or let's say k such vectors where we have the inputs for our neural network. Then what we have with the connections, we have the weights and the bias. So the network consists of connections. We will build the neurons, the network from the neurons, and by connecting them and defining the connections with the subsequent neurons. Okay, so which exactly neurons to connect to. So each connection provides the output of one neuron as the input to another neuron. These connections are assigned weights, so these are the W parameters which you have for each individual neuron. So each input to the neuron has a weight. So it somehow represents the relative importance of the inputs. Of course, a neuron can have multiple input-output connections. So these are the weights, and then we have, of course, this additional bias or shift that is just used to give more freedom for the training. Okay. Then we have the activation. I basically mentioned it already. So this activation is the purpose is to add nonlinearity to our model, so that we can fit more complicated examples, not just new linear tasks. Okay, and then this is basically the output formula. So what happens, what the neuron does, if we look at it from the mathematical point of view, it's simply a weighted combination, linear combination of the inputs. So this is the linear function we have seen in the beginning in one of the previous lectures. And then we apply a nonlinear function to this value to the linear function. So all in all, we can write it concisely in this way. So the neuron basically gets some values and it outputs a number. Okay? And now, where do we have the network? Well, we can now, from this basic building block, we can construct a structure, which we call the artificial neural network. So we are given our inputs. The inputs, the inputs are connected to neurons. The neurons are organized into layers. So we have, we call them hidden layers. So they are somehow inside the model. So we have input, some hidden layers with neurons, and then we get our outputs. So this is.
Sure, small question. In the output equation that you have above, where's the bias exactly?
Where is the
bias? How does the mathematically represent the
W0?
Isn't that that's not the weight?
This is the weight, right? But the weight is not without any input, so it's a number which you add. So it's like a shift to your basic combination, and then you have a shift which shifts the by like a constant. Once it's trained, this is a constant. So this value will depend on the inputs, values. This is independent, so always shifted. So this is the bias, okay?
H state is 0. Okay, no, hold on. H state is 0. Okay, no, hold on.
All right. So then this is basically how we construct our neural network. We put the neurons into layers, and then the input is what we show, and what we will use is a fully connected. This is a fully connected network. So the inputs are connected with each of the neurons in the first layer, and then these neurons are all connected with the neurons in the second layer. And then from that you get the output, and the flow of information is from the input to the output. So that this is the so-called forward propagation. So the computation of the neural network is done by the forward propagation. Given the inputs, we compute the values for individual layers, and then this is propagated from left to right. Okay. Then we will have something which is called back propagation. This will be when we go back to update the parameters, and this is where the gradient is computed and where the optimization is done. So workflow with a neural network is basically compute values from the input, compute the output, compare with the data you have by using the loss function. Once you have this with the gradient descent, you can perform the optimization, so you know how to optimize the parameters. The problem is, for gradient descent, you need to compute the gradient. And the computation of the gradient is done backwards by considering the neurons from input, so because we compute the loss function, so from loss function we see how this function depends on these parameters, and so on. So this is done by backpropagation and by using the chain rule for derivation. And we will not get that much into these details because the idea is quite simple. But when you have the neurons, these formulas become quite long and involved. And the only thing you probably is good to remember is that this is backpropagation because to compute the values of the gradient with respect to the parameters which are here, you first need to have the gradient with respect to the parameters which are in the front more layer. So that's why this is done in a backward fashion. Okay? And
so the weights are updated based on the input and the output?
Yes. So you basically have the input from your pair, let's say, of data. So you have, let's say, x1, y1. And this is another pair, just to keep it simple. And then what happens, you give the x1 to the neural network, and it will output, let's say, x1, and this will be, one. It will output y1 with tilde. It means it comes from the neural network. So this is given by the data. This is what is coming from the neural network. So for the second example, you can say the same thing. And now what you want to do, you have a function which, let's say, looks like this. So this will be, let's say, for example, this loss function could be something like this. So the average distance, y2, for example, I mean just to like square root distance between the values, and this is like average, and you want to optimize this function. So this function will depend what are the network. The parameters are hidden here because these parameters, this can be expanded with respect to the parameters. So the parameters are inside here, and then you can optimize your function with the gradient descent with respect to these parameters. So this is the idea of the training. So you are given the data, and you compare the data, the outputs of these input values, which are given, with actually the ones which you receive from the neural network. So this is what happens here. And I have prepared this. I think it's quite a nice thing. If you want to get some more intuition on these neural networks, you can. I have prepared an example here, and actually this is what answers your question about this linear, non-linear problem. And maybe I will not. This you can maybe look yourself at in your free time. This is not obligatory, but I think this gives you some understanding if you go through this example. But what I want you to show is this playground. So actually this is done by Google. And you can now see how without any coding, just by playing here, you can start to get some intuition on how neural networks work, how they are designed, and so on. So let's just quickly have a simple thing. Let's go for classification, okay? So this is an example, and you can play with the number of hidden layers, with the number of neurons in each layer. So this is a linear problem, guys, right? Can you see why it's a linear problem? So what we want to discriminate between these two types of points, right? It's linear because you can draw a line. It's a line, right? So it's a linear equation which tells us whether if we are above the line, the point should be blue. If we are below the line, the point should be yellow. So here you can maybe do the example I described in the appendix yourself, and we can discuss if you want later. But here I will just give you the intuition. So this is for the input. So you select what do you want to input, and maybe this notation is a little bit confusing here, but basically x1, x2, these are the coordinates. So x1 is x, and so if we have the coordinate system, so x1 is, let's say, 2, and x2 is y, so it is, let's say, 3, so this is okay? And you can select which ones you want to give as an input. Let's say we take this linear example, okay? x1, we give the coordinates, x and y. And what we want to say, is the point blue or is the point yellow or orange? These are squared, so this is x1 squared, x2 squared. This is maybe a little bit confusing, but these are like, you first square the coordinates and this gives you as an input. Okay, and then this is clear, so x1 times x2, sine of x1, sine of x2. Okay, but in fact, you can see here, if you play, that we just have one neuron, and we know that the problem is linear, right? I mean, we can separate it with a line. So this is a rule. If it's above the line, it's blue. If it's below, it's yellow. So here we can change, this is the activation function. You can see here they provide 4 different activations. Let's keep it very simple, linear. Okay, so this means we have no activation function. This is like identity. The activation function is just what we return. And once we have this, okay, learning like this you don't really need to worry about. You can just start the training. And then you see, of course, this went very quickly. Immediately the neuron found a line which separates. And here you can see the loss is almost perfect. This is the number of epochs, so how of the training, so iterations of the training. And this neuron, this shows you the weights. So what are the weights? Is denoted by the color. The color is encoded from -1 to 1, so it encodes the weight. If you zoom over, you can actually see what is the training rate. You can stop the training now, it's quite good. So you can see the weights, you can see the weight of the output, and then of course there is a hidden neuron here, which is this classification, which makes basically the decision. Is it above the line or below? I mean, just takes this output and depending on this output, say whether it's blue or yellow. Okay, so if you later, if you have time, we can go through it together. If not, you can try to see this example. It will clarify the difference between linear and nonlinear. So there I took basically for nonlinear problem, you can take this example. This is what I wanted to discuss in the example, and now you cannot really separate them with a straight line. Right? But maybe I can show you quickly. Okay, let's maybe not go into details. For that, you need basically a circle, and then you will see in the example how you can find a curve which will determine this. But then you need a little bit more complicated neural network and activation function. Either play with the input, you will see it in the description, or give this standard input without any transformation, and then you need nonlinearity to separate this data. Okay, so this you can look yourself.
So the loss like an R value, like the R value?
Yeah, basically it's you have a radius which tells you is it above or below the distance from the origin. So you can play with this. Okay. Okay, so we cover this. I use this notebook because it is, then we will see, we can do a training of a network with a framework, so we can have the code also in the notebook and we can see the results. I just want to check one thing here. Right. This we discussed. And there you can play. Maybe I can show you just one more thing in this. So you can, when we said that we build the network from neurons. So this example shows, okay, we have one neuron now, and what we can do, we can add layers, and in each layer we can add neurons. So you specify how many neurons you want to have each layer, how many layers you want to have, and in this way we start, you see, we start to build a neural network, and these links, they show us connection. In this case, everything is connected.
Well, depending on like how many layers or things like that, there's a line there between origin bullet changes in the background of the...
Yeah, because this is the combination. So it's set, now it's specified as linear.
Yeah.
So it means that these are linear functions. This is a combination of linear functions.
Okay.
And this is one thing. Whatever you would add here, you would always end up with a line.
Okay.
Because this is a linear function.
Yeah.
And what you need to fit this is basically, this is where the activation comes in. You need to change here.
Yeah.
And then it means that each neuron, let's say, will have a hyperbolic tangent as an activation function.
Okay.
And then you will see, okay, I didn't play with this, this is just random. You will see the solution in the appendix. But then you can see that if we leave it, it will take some time. Because now we have more parameters and it takes some time to check. But now you see that it gets accurate. So this is the way, visual, let's say, intuitive way to see how this activation function is important. Because now it can fit. Okay? But you see it and then you see the training process. So it is slowing down. Like, first it's slow, suddenly it improves, slows down, improves. Of course, how long to train, this is another topic.
Yeah.
We will not touch. But you can, so with this you can play and you can get some intuition of how these neurons are working. Okay? And maybe one comment before we switch to the next step. These are simple neural networks in the sense that, and we will today we will focus on those. First of all, neurons are always the same. I mean, this is, the architecture is the same. The thing is, how do you connect these neurons? So here we take all the inputs. I mean, if we consider x1, x2 is all the input, this is connected to all the neurons with the first layer. So we have full connectivity. We will, for the project that we are going to discuss next week, this will not be the case. And this is what is tricky with images. And actually it also has a biological inspiration, that we only look at somehow inputs or pixels that are nearby. So we connect, somehow the connections are limited. But this we will see next week. So this playground is not fully, it's a simple in the sense that you cannot really train any neural network here and it's slow, but it's good enough to get some intuition. Because one thing you can maybe, you heard when talking about neural networks, you cannot really analyze them. That's the problem. So when you have complex neural networks with many layers, you actually don't know what is going on. If you are fitting some maybe complex, very complex function, but these weights and all these values, they don't really tell you anything. But it's not completely true, and this we will see in this example, in the appendix, that you can do some actual reasoning if you have a simple neural network. And what I propose, you can maybe, when you do this exercise, you can check yourself how having this information, that you have this intuition that this is something you know how to solve the problem, how it influences the training. You will see that in the first case, the training is very fast. In the second case, like this one, this will be basically what is proposed as a second solution, you get a good fit, but the training takes much more time. And this we will observe if you can do this. Okay? So this is a place where you can try yourself to get some more intuition and see how this behaves without any coding and these kind of technicalities. You can just, with the knowledge you have so far, you can play here and get more intuition, because next week you will not be able to basically see the neural net. I mean, we will have the model, but we will treat it, okay, it's in a file, it's defined, we will see picture of layers, that's it. Because it's not possible to do anything more. We will just see the high-level architecture, which is usually used for these kind of problems, because people observe that this behaves well, but actually nobody knows what's there, right?
So okay. Agree with this. What are those graphs that correspond to functions, to the activation function with different ways?
Here.
Yeah.
So you can zoom on them, and then you will see that how this neuron is trained. Okay. So what is the line it fits? So it fits a line which is here. The problem is that you have now a 10H, a hyperbolic tangent activation function. So this value is in, because it's x, actually this function is x and y, so it's a plane. And then you have on top of that the tan h, so you have a three-dimensional picture, and then it is projected on the plane, so that's why you get the line. In fact, this is not a linear function, but the projection, you get the zero value, basically.
So those are all variations of the same activation function?
Yeah, so this is like the activation function applied to different points. So it's like a 3D picture, but the 3D is encoded with the color. So the third dimension. And here you can say you don't want to discretize output. So it means it is low here. This is basically zero value, and it becomes like a one value. So it is like this surface is. It will go like, so it is 0, okay, so -1, 1, and then you have something like this. So it has a steep, this near 0 value, and then -1. And this is, you can look individually at each of them. So for example, this becomes a little bit finally more complicated. Maybe smaller values, so the color is not that intensive, but then you see that this shape is more curved, let's say, of these zero values. So the surface, and then you have the zero value and the other values -1. Okay? Right. So, are there any questions for this part? No? It's clear?
On that page, it can describe about the activation differences, for example, to linear and sigmoid.
Yeah. So these activation functions are. So I can quickly explain. Basically, tan H and sigmoid are the same. Tan H is more general, but tan H is I have to see the formula, but they are like a special case of the sigmoid function. So it's like a parameter which you set up, and then you get tan H. So basically, the shape of the sigmoid function is something like this. Okay, it should go to 0. So it maps. The idea is that it maps the real line between -1 and 1. This is the sigmoid. Relu, it means that you have, when it is negative, it's always 0, and then it is like identity function. So this is the relu. Sigmoid is this, tan H is similar, it's just that the curve is, you can play with the slope, let's say here. And the linear means nothing. So linear means identity. So you apply, you don't, like you would have no activation function.
And what's the connection between how can we apply in which case we can apply?
There is no clear answer. So this is by case, like case dependent, and you have to kind of investigate which function is proper for your problem. So there is no clear answer. There is no clear answer what kind of function to use, activation function to use, how long the training should be. You will see in a moment another parameter, which this is another kind of research. What you can do when you do this exercise I mentioned, you can try to have the same network structure and try to play with, because it should work with any of those. So you can use Reno, I think I brought it there. You can use sigmoid, you can, just it's not non-linear, so don't use linear, but any of these three should be fine. Reno, sigmoid, and action. But what you can see when you have a given, fix your architecture, you use different of these, you will see that this influences the learning time. That's the thing. You will see that some are faster, some are slower. Which one to use for your problem? Basically to experiment.
Because theoretically we could just have one type of non-linear activation function and we could use that to solve any non-linear problem.
Yes, yes. Provided that you have enough neurons and layers, because this will probably, it's not enough to have, in this particular example, it will not enough to have one neuron or even two neurons with non-linear function. You need three, I think. At least this is what I observed, that for that you need probably three is the minimum you need to with non-linear activation to solve this circular problem.
So different non-linear activation functions optimize the neural network in different ways.
So once you select the, of course, in this framework, you select one, so all neurons will have the same activation function. But yes, they are because there are also these weights, and these weights will influence the behavior of it, because these weights influence the input to the signal, the argument of the function. So each neuron will have different weights, so it will have a different value for the same input, and it will give a different output. But this is like you combine these basic building blocks, and you get different outputs, and finally you can find this complicated function for your problem. This is the main idea. This is a take-home message from all this introduction. Okay, so very basic building blocks put in a structure and then combined with all these learning algorithm, basically gradient descent, allows us to fit the model to our data. But this is, of course, ideal situation. The problem is that, of course, this depends on what exactly is your architecture, what is your number of neurons, layers. This is case dependent. Okay. So maybe what I propose. Okay, let's maybe start on this. So we will now see how we can. We will analyze a case study with real data. We will try to build a neural network for that. With some framework. So now, this cannot really, I think, be solved with what I was with this playground, because it's kind of a simple thing. This is more flexible. Maybe you could also, maybe it's not that complicated. Maybe still you could choose, you could try to also implement it in the framework if you want. The only problem is that with the framework you probably cannot give the data. So they have fixed data sets. So that's why you cannot really run it there. But we will see now how you can do it in Python with some library which is called Chainer. This is a framework for training neural networks. It's not the only possible framework that we could use. There are a number of others. So you could use PyTorch, Keras, TensorFlow. All these are frameworks which can be used for with Python for training neural networks. I think there are some, let's say, philosophical differences between these frameworks. How do you, what kind of programming paradigm they assume, and how this works. But in general, from, let's say, a usability point of view, all this is equally good. There are maybe some differences in performance. If you are interested, you can check the benchmarks and so on. Chainer is not the most commonly used framework nowadays, but we will look at it because it's quite clear, it's quite easy. And the first thing, second thing, it will be used by the project that we will look at next week is implemented in Chainer. So just for convenience and that you get familiar with this in an easy way, because in this project there are more things. So we first want to give you just an overview. How do you work with, how do you build and how do you train a neural network when you have to do it, let's say, yourself, okay, from scratch, more or less. So, but one remark, I think TensorFlow is one of the top frameworks nowadays. It's developed by Google. And on top of that, because this is like a low-level programming, you have Keras, which is a kind of built on top of TensorFlow, and then I think it kind of resembles Chainer, that you can, in the terms that you can use some high-level commands. You will see that there are some layers you can specify with one command, and I think Keras is exactly the framework which has similar high level of introducing or constructing the network. And actually the playground is done by Google. It's not in TensorFlow, so it's not that efficient, but you can, but if you want, nowadays, I think TensorFlow, right, is the most commonly used. So you can also, if you want, you can look at this one. But the philosophy, the idea is basically the same for all of them. Okay. So as a case study, what we will look at is some analysis of the ionosphere. Okay, so it's very simple. The data are, you can click on the link. You can find that this is available, online available data, and it is. So you can find a more detailed description here on this website. I have already, you can download the data file somewhere. We provided the link in a moment. You can see it, and you will also have it put on Moodle. So the idea is that we have some radar data which considers which targets the free electrons. So there are free electrons in the ionosphere, and the idea is, as far as I understand, because I didn't really see all the details of what exactly each particular measure is, but the idea is that they have some system of high frequency antennas which are sending the signal to the ionosphere, and the idea is that if there is some structure, then this structure will cause the beam to be reflected, so the signal will come back to Earth, and then somehow it means that what they say, that the ionosphere is good. Okay, so this is a situation where we have some structure in these free electrons in the ionosphere, and we say, okay, so these measurements should be considered as good. This is a good case. On the other hand, if there is no structure, the signal will just penetrate the ionosphere, it will be not reflected, and then it means that basically there is no structure, so the case is, this case is, let's say, bad. Okay, this is how they encode it in the data set. So this is a binary classification problem. Either the case is good or it is bad. Okay, and we have now 34 continuous input variables. So actually, these are the measurements. So this is what is measured by the radar, what comes back. So they put it in a, you can maybe see it here, in a column. So this is the data file, and then each row is one case. So these are these 34 numbers. They encode the measurements from the radar data. If you're interested in the details, you can check this data description website. And the final column is the class. So this is good and this is bad. Okay, so the first case is good, the second one is bad. And what we want to do, so we want to train a network or have some model which will do it for us automatically. Okay, so the idea is that once you are providing the system with a measurement coming from the radar, this value will be kind of given to us automatically by our model. And of course, we want it to be a good model so that this is realistic. I mean, we don't have to do it by hand, analyze these things, but we can just provide it this data into our model, and we will get this classification automatically, and it should be of reasonable quality. Okay, so this is the idea. So this is the data set that we will use. And this is a standard thing. So what we normally do when we work with Chainer, when we want to construct our neural network, we have to import some libraries because Python is like an extension to Python. So we basically load the Chainer in this way. We will see in a moment these elements, so they will be used throughout the code. We will use them to make the training. So we basically input Chainer, we input data sets, and so on. So functions, links, these will be used for actually constructing the neural network. So now you can basically hopefully.
I'm not using notebook, I'm using lab.
Oh yeah, you can use any.
Because I couldn't load the images on the notebook.
You couldn't.
No, I put them in the correct path and they appear in Jupyter Lab and not notebook.
Ah, I see.
But the code should work on both, right?
Did you download this image folder?
None of the images appear on the on lab, so they're where they should be.
Right. Okay, so this you just know. I mean, it's nothing. If you get an error, probably you need to install Chainer.
Yeah,
And-
I think we didn't.
So you need to, if you use Anaconda, you can write conda install Chainer. It might ask you for some dependencies, so you just accept, or then I think you can just install Chainer. So this is another option if you have. It will install with the Python. So you can try it yourself which one
On the front.
and see which one to.
Where
this-
is the prompt?
Where it was?
In the terminal.
Oh,
So you go to command line terminal
yeah.
and then you type in this command. Either conda, maybe you need to put. I think for conda you don't need your super user
We don't need
password.
to close.
Collect the chain, yeah.
No, we don't need to close anything. We can do.
No, I think you can just from the terminal and then you restart, like you try Jupyter, like you click on run again.
Okay.
Well,
It should work.
It adds all the packages this way. Does the second command add? Oh, okay.
I think it should install also the dependencies. Like it will ask if you want to install the required dependencies.
That was just a GUI.
So you either this or this should. Sometimes there is a problem because, but if not one, try the other one.
Because I successfully built Chainer, but maybe it's an error. Distributed 121.8 requires MSG package and installed.
What if you try the other one?
Yeah.
Or it also depends how
Sorry, what's that? CO?
PIP
Not the first.
conda. If you use Anaconda, then you have it. If you don't have Anaconda, you will not have this one.
So you can open like Anaconda and like environments.
Here?
Environments, yes.
Okay.
And so you have installed in this install section, not installed. And search packages. No. Yeah.
Here.
There. Chainer. Select Chainer. And apply.
Okay. This is another way.
If you cannot use the conda install chainer method, you can do it from like Anaconda Navigator.
Yeah.
Because some students have no, I think, Mac OS or Linux. They have some Windows versions.
Right.
So they cannot use conda install chainer.
I see. Okay.
But everyone can install any package using this Anaconda Navigator environments.
So yeah, this works for macOS and Linux. Yeah, Windows
I think you can do it in Windows too, but
with command line,
yeah.
but that's maybe not very.
Yeah, it didn't work with command line.
And then you have to please apply.
So,
In the end, apply.
alright, so then this is for installing chainer, and then because we want to have some display some statistics of the training process, we will use matplotlib.
Oh, okay.
So you can also import matplot. So this is
There it was.
Yep.
I didn't have to close it.
Did anybody use it or not?
Oh yeah, thanks. That's too much. Now there's another problem. Future warning conversion of the second argument of E should be typed from the flow to. It's about something. It's a future warning.
Okay.
I'm sure it doesn't include some obscure programming.
But if it's a warning, maybe you don't really need to. I mean, if it's not an error, it will
No, it's a future warning.
future warning. It can be also depending on what version of Python, because that is 2, Python 2.7 and 3. I'm using Python 3. If you use Python 2.7, there could be also, because they are not, if it says future, it's probably 2.7 and it uses the.
If you use it kind of free.
Sure. Oh, you know that.
For the
Yeah, that's
matplotlib, in the instruction, you use quote, or ag, is that aggregate, what does that mean?
No, so actually I was also confused. This is what kind of output format. So we will use PM, use the image, the file, will be saved in the PNG format.
It's something about
I didn't say AG.
And I don't remember, you can check. It's not very intuitive. I think you can, but actually this didn't work for me because I tried PDF, then you can write PDF, but it still generated PNG, so I don't really see how this exactly works. You will need to check the documentation for the exact parameters, but it also probably has to do something with the environment, the operating system you are using. So this might not work. It should work on all of them, but somehow there is might be, because it's like a graphical output, so it depends what kind of interface you have for. Like on Linux, you could have different like Qt or some other frameworks.
Then you have to bug.
And
Then
this is basically the output, format of the output.
again
Graphical. So we will see.
start reload
But sometimes
this
for Mozilla it's okay.
file and try again.
Okay, so you see another protocol. Okay.
It should be working now, but I don't know.
So maybe let's continue for a few minutes and then we will make a break. But here what I want to explain is the general structure of how this whole framework works and how you get the basic or the important elements of your neural network construction and training. So what we are going to use, the trainer, which basically consists of 2 parts, updater and the extensions. Extensions, this will be used just for reporting. So when the training is running, we will output some pictures, some graphs, some logs. This will be specified here in this part, in extensions. And actually this is done once everything else is specified. We will add the extension so we can treat it a little bit aside for a moment. What we need to focus on is the updater. So actually this is the element of the whole architecture or the framework which performs the optimization. Okay? So in order to perform the optimization, 2 things are needed. Particular optimizer, which one we want to use for finding the good parameters. And we have to have an iterator which will go through the training samples. The iterator works on the dataset. So the dataset will be specified here. Once we have the dataset, we will define the iterator. Similarly, you have to have an optimizer. So the optimizer optimizes the parameters of a model. So first we have to specify the model. And in our case, this is the neural network. This is where the neural network architecture comes in. Once we have the neural network architecture, the parameters are implicitly defined. We will see in a moment. And then we give this model to our optimizer. So the whole idea is that we build from these most inner elements, and we will go up the hierarchy to construct the iterator optimizer, then give this to the updater. For the trainer, you will provide the extensions, and then we can run our network and perform our optimization and learning of the whole thing. Okay, so this is the general outlook, how we should think about the code which is coming. And actually, this is also how you should think when we see the code next week, which is more complicated, but it follows basically the same structure. Okay, so
I can see the image on your screen for now, but if I want to look at these at home, I can't see the image for some reason. It's not appearing.
Maybe.
For now, it's fine, but.
Remember when we had to put percent inline at the top?
I tried running. It doesn't appear. For now, it's fine, but I might want to look at this at home. And
sure. Maybe we can we look at this during the break?
Okay,
we can try to fix. But you are using you said not Jupyter Notebook, Jupyter Lab. It should be this.
When it's not finished,
Because these
you have to
images
back to
are
the
as
code.
HTML links. So it's just if
Then
this
stand
editor
again
can.
oh, it's not an image in this case then.
It's not like you have. It's a link
And
which
then
tells where the
open
image
this
is.
new
So
window.
it is probably
with
because
this
of
file.
Let me check it.
of that. Because this is the image. It links to this
this
folder. And the
lecture
images
file.
are in the folder.
But this
Find
one's
the
not there.
lecture file, exactly. Yes.
And
Oh,
And-
let's see.
and
Okay,
then
I will
this
correct
one.
this. Okay, now I see. Yeah, I see the
This part
problem.
is
the other side
it's running.
Yeah.
down
This
the
one.
floor.
Okay, this is the problem in the.
I have an updated version.
You update it. Can you please update the links? Yeah. Okay. So we will update on. This is the problem. How I include this.
No, it's fine for the others. It's something with my
China. You have to put it again.
It's fine. You can look at it over the.
Yeah. Okay. I will and change it. Will upload.
Yeah.
Correct.
China again. Elements, not
So yeah, this is with the links. Sometimes they are. I think it's cached. That's a problem. Sometimes it gets cached. And
Yeah.
then I
Don't
see it. I don't see that there is a problem. But we will correct it. Please report if there is any. You have seen any problems with the images. We will try to fix it. Okay. So this is the general framework. And let's maybe stop here. Maybe we have a 10 minutes break. So let's say we meet 5:35. Okay. And then we will basically follow this picture and build our network and train it.
It's working. No, don't worry. Okay, it's here is not. We're trying to do it starts, there is no error. But you, by you, it's generated some errors. Yes?
Yeah, we do.
But you install, then you have to back to home.
Schedule session.
They should be. That's put their installs and should be on the list.
Because I would love to hear that right now. That would be pretty great.
Is the China?
Yeah, 9.
It should be. Yeah.
Let me check. For me, it's a one-day thing.
Strange.
Come on, fucking.
Yeah. But now if it's any, that it would some information about the that's installed successfully.
Yes.
It was.
Yes. No,
But there-
no, it didn't show.
Okay.
It's just to install this one.
Apply.
You say and it's just a word now. It's here. It didn't show anything for the install success.
Yeah. Okay.
Landed in IT.
You were the lucky guy.
Fetching or it will be same start now.
So you had leaks, you had everything.
Yeah. I don't know what happened.
But we had admin this and that was more than
You got it? You looking at the microphone?
Oh, come on.
One second. Back.
No, we have classes tomorrow after.
Yes, we have.
Morning and after.
Morning and the afternoon, yeah. No mercy.
you can use
I
every
also
room.
like
You can use every room.
So I should ensure my
Check. You can. Pause it. At the rate, uni.lu.
And you, this is like great, I think, as professor, the way you like
I wrote right in the.
yeah, I know, but the wrong guy, I agree with you.
That was like.
Yeah.
And happened even when he was not there. You know?
No,
Yeah,
he was.
yeah,
Oh God, I was down.
yeah.
I think it's working out. Yeah.
So
Now
far
I can
it's-
try downloading it and pausing it. It's okay because you download quite quickly. Just remove it and download once again. The 64-bit one, but it'll be quite faster. Is it nine? 47. So you were using it. Just asked if it was. Why waste it user?
No, actually.
But the data speeds suck in this
Yeah,
country.
exactly.
Hey, what happened to her business card plan?
What is a business card?
She was planning to make the design.
Yes, but she has no time. She will do. She
Yes.
said that. I mean,
So
if
I
all of
go to
us.
the Amazon building to help them because they do
The syntaxes. Show you.